So we have obtained the relation between pressure of the gas and velocity, or average velocity squared of the molecule. The next thing I want to do is to combine this result with the ideal gas law to see if we can find some new understanding of the gas. Write down the ideal gas law. Now the ideal gas law is PV is equal to nRT. So let's see how we can combine them. Right, I have P there, which is fine, but what about the V and RT? Can I relate it to any of these? Oh yes, I can relate it to rho. Okay, so rho is related to V, if you remember that rho is actually equal to mass over volume, mass of the gas over volume, and mass of the gas is let's see, is the number of molecules multiplied by the mass of one molecule. Okay, so that's the mass of one molecule. Yeah, and we have the V. That seems okay, simple enough. So let me put this into here. Right, so actually it was in this form in a previous session, so I'm just reverting to that form. So P then is equal to 1/3 rho would be that, so N M over V times C squared averaged. Okay, now if I compare this with this, okay, you see that there's some hope here. I have V here and a V here. So let me move the V over to the other side. So PV is equal to 1/3 N M C squared bar. The reason why I want to do this, so I can make use of this relation and relate it to something different from what I have here. In this case, you see that we can actually relate it to the temperature. So therefore, PV is equal to nRT, and I can substitute that into the PV here, nRT. Okay, so far so good. Now what do I want to do? Okay, what I like to do is this. You see this MC squared here. Okay, we have the bar here, so M times the average of velocity squared. Now what does mass times velocity squared remind us of? Something that we have learned in a much earlier session. Something involving mass times velocity squared. Now if I add a half there, wouldn't that be kinetic energy? So that's it. That's what we've learned much earlier. Kinetic energy. Right, so I have an expression here, mc squared with the average. So wouldn't it be nice if I can write this in terms of the average kinetic energy of the molecule, and then I might even have related to the temperature of the gas. Energy of molecule, temperature of gas. That's a nice relation, right? That's something new, something we have not seen just now when we look at the gas law and this this pressure calculation separately. So let's try and do that. So what I like to do now is to arrange this, so that I have the kinetic energy on one side. So I have mc squared here. Now I like to have a half, and I like to get rid of all the rest of it. So let's see what I can do. So first, let me move this log over to the other side and just keep the mc squared on the right. So 3 comes up here, and after nRT, and the n comes down there. Okay, that's right. So then I'm just going to add in the half. I'm just going to multiply both sides by half, up there and 2 there. So there, we now have a formula relating the kinetic energy, average kinetic energy of a molecule, with temperature, and I have all these other constants there. That's the ideal gas. There's the gas constant, which we know, 8.31 in SI units. Number of moles, we understand that. Number of molecules. Okay. But what I want to do now is I want to make this a little bit simpler. Okay, I want to simplify this a bit more. There are still quite a number of symbols here. So the way to simplify this part is this. Now this part here, let me focus on this for a little bit. The n here, the number of molecules, is related to the number of moles. If you recall, the 1 mole means the Avogadro constant number of particles. Okay, so n mole therefore would mean n times Na particles. So in other words, this must be equal to the n down here. Okay, this must be equal to the total number of molecules. Right. So let me just pull that out and see if I can simplify that a little bit. So nr over n, big N, is small n over Na. Right, and so you see that we can cancel this n here and here, and we have just r over Na. Gas constant divided by Avogadro constant. Now in physics there is actually a name for this ratio and a symbol. Now the symbol is Kb, and the name is Boltzmann Constant. Boltzmann Constant. So that simplifies this. All right, instead of I'll simplify the writing anyway. Yeah, instead of nRn, instead of these 3 symbols, I can just replace that by just one constant, Kb. And important thing is that it's a constant. It doesn't actually depend on the number of moles or the number of molecules. Okay, because the ratio of the number of moles and the number of molecules you've seen from here is actually just 1 over Na, which is itself a constant. So this whole thing is just one constant again. That's Kb. Okay, so finally we have our relation. We have half mc squared kinetic energy, average kinetic energy of a molecule is equal to 3 over 2 times kb times T. So write this out. 3 over 2 times kb times temperature. And that's an important relation that we have now obtained.